Welcome to Math with Michelle, where math finally makes sense. Whether you're tackling high school math or diving into college algebra, I'm here to break it down step by step with real examples and zero stress. From algebra to functions, graphs to equations, I've got it covered. Hit that like button and let's master math together.
So you're working in your geometry class on kites with trapezoids, but most of us probably remember what a kite is generically, but it has a lot of key features, and then we'll get into trapezoids in a minute. So you probably remember as a kid going ahead and you got this little bitty plastic bar and you put it like this. Then you had a secondary plastic bar and you put it like this until they made like a T, right? And when you put those two things into the little pockets on the back of your kite, you're able to go ahead and attach the string on the bottom and go fly. Well, some important things to know that in a actual mathematical kite, maybe not the kite you flew, who knows what kind of extra, maybe you had a dragon-shaped kite, I don't know. But in a traditional kite, where the diagonals come together, it's a right angle. Furthermore, the top left and the top right of the kite are congruent, and the bottom left and the bottom right are congruent. And we could prove this now by the hypotenuse leg theorem. You can basically fold and reflect, things like that, but that's going to be our true definition of a kite, okay? So you have to have two pairs of congruent sides. And these are going to be adjacent to each other, right? Your diagonals must be perpendicular, okay? And the other thing is that because of this, everything's going to match up on the top. Like triangle 1 is going to be congruent to triangle 2, and you can go through that, they share that leg, hypotenuse matches, so corresponding parts of congruent triangles are congruent. And triangle 3 and triangle 4 are also going to be congruent. That also means the big triangle on the left, when you put 1 and 3 together, is going to be congruent to the big triangle on the right when you put 2 and 4 together. Okay, so let's go ahead and give some variables here, or name these vertices. So if B to D equals 10, does BX equal 5? Okay. So BD is from here to here. So I forgot to put my X on there. That would be confusing. So if B to D is 10, is B to the X 5? Well, this is an isosceles trapezoid, and this is an isosceles trapezoid. However, X is not the midpoint from top to bottom. Okay, however, if AC equals 8, does AX equal 4? So A to C equals 8, so does A to X equal 4? And the answer to that is yes, absolutely. And it has to do with, this is a perpendicular bisector that goes to the vertex. And if you know about a perpendicular bisector that goes to the vertex, it means that they're equidistant. Also, the word bisect is a big deal. So this version is a bisector because A to B and A to C are equidistant, that means A to X and C to X are also going to be equidistant because we have perpendicular and we have these being congruent. That means they are equidistant. Here, this was not congruent to this. That's why we had the no. So we just have to make sure we understand which one is which and use them accordingly. So there's not much more to kites, but it is really important to know that their diagonals are perpendicular. Okay, two pairs of congruent sides, boom, these adjacent ones, boom, these adjacent ones. And the diagonals are perpendicular. Okay. Now, what is a trapezoid? I find students forget what a trapezoid is a lot. So we all know what a triangle is, right? There's a triangle. Here's a triangle. Okay, I did this purposely, I promise. So what if we were to just cut off the top somewhere parallel to the bottom and keep what's left on the bottom? Now we have a trapezoid. So again, we're just chopping off that top, parallel to the bottom. And that's a big keyword, parallel to the bottom. Okay, that's a trapezoid. It is very important that you know that trapezoids have one pair of parallel sides. That's the definition of a trapezoid. Four-sided shape with one pair of parallel sides. Four-sided meaning quadrilateral. One pair parallel sides. If it had two sets of parallel sides, it would be something else. That's why I kind of say it's a triangle with the top cut off of it. So lots of relations come in here. Now, if you think isosceles triangle, which I kind of had an isosceles triangle drawn here, right? Let's go ahead. What do we know about isosceles triangles? If this side's congruent to this side, then this angle is congruent to this angle, right? So if we cut the top off parallel, we still have the same information because we cut it off equally from both sides. So not only is this a trapezoid, this is now an isosceles trapezoid. Okay, so keep that in mind. How do we know that it's an isosceles trapezoid and that all those things stay true? So let's go ahead and let's look at what we've got here. Okay, we're going to find out all the key features of an isosceles trapezoid. So I'm going to draw this really lightly in pencil so that we can really focus in on stuff. Not too lightly in pencil, but. Okay. So I've given this, and I'm going to give us this and this. So A, B, C, D. Okay. So we know AB is congruent to CD. We also know that BC is parallel to AD. Okay. So let's just think about this line right here, this line right here, and this line right here, with this angle and this angle. What do we know? Well, we know parallel lines cut by a transversal, that when the angles are on the same side, but in between the parallel lines, so interior, are supplementary. Which tells me that angle A plus angle B would be 180 degrees. Could I do the same thing for C and D? Absolutely. So that's something, technically I should say the measure of angle A, measure of angle C, measure of angle B, measure of angle D. Now, I'm going to go ahead and turn, I don't want to use orange again. We're going to make this triangle. So triangle A, B, D. Now notice I'm not using the full angle B here that I mentioned here. So that's important to keep in mind. And I'm going to do triangle A, C, D. Okay. Now, because of isosceles, we also know that the measure of angle A is congruent to the measure of angle D. And we know that because isosceles. And I reminded us this, whoops. Okay, so we know AB is congruent to CD. We know angle A is congruent to angle D. Only B and C were the ones that cut. So remember, in the green triangle, we're using all of angle D. And in the brown triangle, we're using all of angle A. So keep that in mind. And see how they both have side AD? So what have I marked here? I've marked side angle side. So we go side angle side or side angle side. So these two triangles are congruent because of side angle side. And the bottoms were the same because of the reflexive property. So if the bottoms are the same, and we can say they're congruent by side angle side, then what else can we say? We can say the triangles are congruent. And if the triangles are congruent, then wouldn't BD have to equal AC? Because corresponding parts are congruent, triangles are congruent? Absolutely. AC is a diagonal, BD is a diagonal. So in an isosceles trapezoid, the diagonals are congruent. Will that happen in all trapezoids? No, just the isosceles ones. Okay, so let's look at a generic trapezoid, one that is not isosceles, and we're going to look at one other relationship. So I'm going to put a third line in here that is parallel to the bases. Okay, so remember, however big this angle is and this angle is, they're going to be congruent. And the reason is when you have parallel lines cut by a transversal, the corresponding angles are congruent. So therefore, however big this angle is how big this angle is. And could we do the same from here to here and here to here? Absolutely, yes. We can get all those angles. If we know one, we can really get all of them because of parallel lines cut by transversal. The bigger thing with this trapezoid is I didn't just go ahead and draw a third line. I drew a third line that happened to bisect the sides. It's parallel, so it has to cut them equal. Now, keep in mind that this side is not necessarily the same as this side. So let's say this entire side had a height of 8. These would each be 4. And at this side, see how it's slanted a little bit more? Maybe it had a length of 10, so these would each be 5. Okay? So that's something that's kind of big to know, is that whenever it's parallel to both sides, if it bisects one side, it bisects the other side. It's called a mid-segment. Okay, so what if we have this scenario? Parallel to parallel to parallel. Okay. A, B, C, D. I'm going to call this X and this Y. The length of AD is 20. The length of BC is 12. What is the length of XY? Well, it's obviously got to be more than 12 and less than 20, right? And because everything's a mid-segment, there's got to be some kind of relationship of the middle or the average, and that's exactly how we're going to find it. To find the length of that middle section, you're just going to take the bottom plus the top, divide by 2. That's going to actually be the rule. It's the average year basis. I don't like memorizing formulas. I like thinking of the relationships, and it's like, oh, well, hey, it's the middle, so it's the middle of these numbers. So how can I find the middle? I'm just going to add them up and divide by 2, which is 4 away from each. So that makes sense. So there's a lot of relationships inside these angles and things like that, so we need to just be careful. Knowing whether you have parallel lines is a very big key. So kites, no parallel lines. Nothing was parallel. Trapezoids has one side of parallel sides, while kites had 2 pairs of congruent sides. So make sure you keep your shapes straight, and you should be golden.
Thanks for learning with me here on Math with Michelle. If this helped, give it a like and don't forget to subscribe for more clear and simple math lessons. Got a question or topic you want me to cover? Drop it in the comments. Until next time, keep practicing, stay curious, and remember, you've got this.